Dear students, in last section we had studied about the types of solids and how they behave under the external influence of the force. Now we will see that what is that elastic behavior of solid. Here in this topic we can explain that elastic behavior of solids. Now we will see that what is the topic consist. We have very well knowledge that in a solid each atom or molecule is surrounded by neighboring atoms or molecules. So it is very clear that each atom is surrounded by, this is very well known that each atom is surrounded by neighboring atoms. Now in place of atoms we can write molecules as well. Now these are bonded together by interatomic or intermolecular forces. So if there are atoms, we can say that atoms or molecules. Okay, so we can put so here they are bonded I would use word tightly by interatomic or intermolecular bond. So they are bonded by interatomic or intermolecular forces and stay in a stable equilibrium position. To remain stable. Now, what are the main reason of their stability? So, when a solid is deformed, the atoms or molecules are displaced from their equilibrium position, causing a change in the interatomic or intermolecular distances. So when deformation force is applied, we can say that when the deformation forces are applied, the distance between them changes. Now when the deformation force is removed, the interatomic forces tends to drive them back to the original position, and when it is released, then interatomic or molecular forces tends to bring original condition back. means they have the tendency to get their original old condition back. Thus, the body regains its original shape and size. Regain its original shape and size back. So this is the process through which the general normal solids gets their original shape and size back. The restoring mechanism can be visualized by taking a model of spring ball system. That is, a spring ball system is like, here we can consider a ball. It is tied to a spring, then another ball, then that is also tied to a spring, then another ball, then it is tied to a spring, a ball, then another spring and ball combination. This type of combination will go on a multiple way. So here the balls represent atoms and spring represent interatomic forces. So if we say that this is atom, this will be interatomic forces. So if you try to displace any ball from its equilibrium position, the spring system tries to restore the ball back to its original position. That means if you try, we can say here that if we try to pull this system in a manner like the condition, say here, suppose we have applied some external force on this atom to pull it, then it will be stretched. So if you try to displace any ball from its equilibrium position, the spring system tries to restore the ball back to its original position. So this is F external. I can say that I am applying on it and it displays its position. We can say that initially it was like this, now it is, after some time it is like this. But when this force is released, then the condition will try to get its form back. So here it is clear that the elastic behavior of solids can be explained in terms of microscopic nature of solids. Robert Hooke, an English physicist, performed experiments on spring and found that the elongation, that is change in length, produced in a body is proportional to the applied force or load. So, Robert Hooke, who had discovered a very important law that is called Hooke's law also, that is Hooke's law. And what is that? He derived that elongation or change in length. So we can say that change in length to the spring like object change in a length for spring-like object is directly proportional to the applied force or load. Directly proportional to the F external, that is external force or external applied force or load. So if we say that the displacement or the change in length to be a delta x or x, so it is, suppose delta x is a change in a length, we can say that it is directly proportional to F. So sorry, that change is directly proportional to F. So here we can say that this F external is directly proportional to the change in its length. So vice versa is possible. He presented his law of elasticity, now which is known as Hooke's law. We shall study it also in our next sections. Now this law, which is like Boyle's Hooke's law in little bit detailed manner, that what it tells about the external force. So before going to that, we have to understand a new topic, that is stress and strain, but that we will discuss later. Right now we will discuss about Hooke's law in very short. So we can say that this is Hooke's law, and what does the statement belongs to it, that stress and strain take different forms in the situation, and for a small deformation the stress and strain are proportional to each other. So here the constraint is put that for small deformation, for small deformation, for small deformation the stress and strain are proportional to each other. To each other, and therefore this statement is called Hooke's law, which is called Hooke's law, which is called Hooke's law, and the statement is stress is proportional to strain, and that means if we remove this proportionality sign, we can say that stress is equals to any of the constant into strain. Now if we explain this K, here we can say that K is this proportionality constant, and it is known as a modulus of elasticity. So it is called modulus of elasticity, and therefore however there are some materials which do not exhibit this linear relationship. So this equation gives us the relation that is linear, and here this is only applicable for small deformation. So for this small deformation, stress and strain are proportional to each other, which is called Hooke's law.